In this video we're going to look at some straightforward uses of Pythagoras' theorem. If you want to see a proof of Pythagoras' theorem, then look at the video that's included in the trigonometry section. Pythagoras' theorem applies when you're working with right-angled triangles. So if we look at a right-angled triangle, it has a 90-degree angle in the corner there, the left-hand corner, and we're going to label our triangle A, B and C. Given that, we know from Pythagoras' theorem that a squared plus b squared is equal to c squared. That's a relationship that's true for all right-angled triangles. We can use this fact to help us work out areas and perimeters of different triangles, not just right-angled triangles, and we'll look at some examples to show exactly how this works. Let's move on to our first example. This triangle is a right-angled triangle and its area is 24 centimeters squared. The question is, what is its perimeter? You might think that's quite a tricky question to answer given that we've only been given one of the lengths of the sides. Working out its perimeter requires us to know all three sides. So what do we know? We know the area of a triangle is half the base times the height. So we've been given the base and the area, so that means we can work out the height. So our area is 24 and that equals a half times 6 times the height. So if we multiply that up by 2, we get 48 equals 6 times the height, and that lets us work out that the height is equal to 8 centimeters. Okay, now we have two of the three sides. If we have two of the three sides of a right-angled triangle, we can use Pythagoras to work out the third. So c squared, our missing side, is equal to the square root of 6 squared plus 8 squared. That means that c is equal to 10. So the perimeter is 6 plus 8 plus 10, which equals 24 centimeters. Okay, let's look at a trickier example now. We're given an equilateral triangle, and we want to find out the area of this equilateral triangle. We're given a piece of information which is that the base is 6 centimeters. So we know, because it's equilateral, all the sides are the same length. We also know that because it's an equilateral triangle, if we draw a line down the center, we end up with two identical right-angled triangles. And because they're identical right-angled triangles, we know that the base of each of them is 3 centimeters. So the height of our triangle can now be calculated using Pythagoras. 6 squared is equal to 3 squared plus h squared. So we rearrange that. We get h squared is equal to 6 squared minus 3 squared. H squared is 36 minus 9, which gives us h is equal to the square root of 27. So the area of the triangle, and we know that the area of a triangle is half the base times the height, is a half times 6, which is the base of the original triangle, times the height, which is root 27. And that turns out to give us a solution of 15.6 centimeters squared for the original equilateral triangle. So questions involving Pythagoras are never that difficult, as long as you can remember the basic equation of a squared plus b squared equals c squared, and that you're able to rearrange that once you've put the values into it that you know about. The difficulties arise when you're given examples like this one, where it doesn't appear initially to be a right-angled triangle. You have to use the diagram and your knowledge of maths to create right-angled triangles within it. Similar questions usually involve isosceles triangles. Once you've recognized that and you can find the right-angled triangle, applying Pythagoras is very straightforward and just relies upon you being able to square numbers and find the square roots of them. Again, as with all problems of this kind, write down all the steps you're taking so that you don't miss any of the numbers that you've worked out along the way.